Dear students, in this video lecture we are going to compare the slope of adiabatic as well as the isothermal process. So by the way, always understand that whenever we discuss about any of the processes in thermodynamics, we deal with ideal gas. And while dealing with ideal gas, we can always use PV is equal to mu RT, whatever the process may be, correct? But for different processes, we have different formulas. Like when we talk about isothermal process, let's talk about isothermal process graph first, and then we'll be talking about the adiabatic process. Okay, so when we talk about the isothermal process, the temperature T is constant, and then remaining two quantities which we have are the pressure and the volume. So what do you think, what will be the relationship between pressure and volume if T is constant? So we do know that pressure will be inversely proportional to the volume, or you may also say that P is equal to some constant K divided by V, or we can also say that PV is equal to some constant K. This law in physics is also known as Boyle's law. Alright, so when we talk about the Boyle's law, we are indirectly applying the isothermal process. Alright, now let's differentiate, or let's apply the chain rule and find the change in both of them part-wise. So P dV, we are taking P constant and then the change in this one, plus we are taking this constant and then we are going to take the change in the pressure. That is equal to no change in the value of constant, so that means 0. So now let's take this on the other side, or any one of the quantities. Let's take V dP, let's keep this over here, and P times dV on the other side, so minus. Okay, now let me draw a graph of P versus V. So what do you think, what's going to happen? When we draw the graph of P versus V, they are going to be inversely proportional to one another. And why it is like that? Because pressure and volume are inversely proportional to one another. Okay, so the graph is going to be something like this. We do know in maths that when two quantities are inversely proportional, the graph is something like a hyperbola, right? Like this one. Okay. This graph is not going to touch any of the axes, because when V is 0, P tends to be infinity, and when P tends to be 0, V tends to be at infinity. So the graph is going to bend something like this. Okay. Now, if I talk about any one point, the graph has some particular slope with respect to x-axis. All right. Now, this slope of the graph is given by change in y-axis divided by change in x-axis, that is dP by dV, that is the slope of the graph. Okay, now if we are supposed to use this particular equation, then dP by dV, that is equal to minus P by V. Alright, so this basically, this value is the slope of this particular graph, so that is minus P by V. Alright, so you can very well see that the slope itself is negative, and that is the ratio of pressure and volume. Okay, now in the same way we are going to apply the concept for the adiabatic process. Now in case of the adiabatic process, we basically say PV raised to gamma is constant. I'm not going to go deep into this particular part, but please note that when we apply isothermal, when we do the numericals related to isothermal process, T is constant, you have to remember this part. This can be also abbreviated as P1V1 is equal to P2V2. But in case of the adiabatic process, PV is not constant, PV raised to gamma is constant, where gamma is the ratio of Cp and Cv for any particular given gas. And you can always this equation here or here, because the gas which we are dealing in this or this process is always ideal gas, and you can use this one. But the standardized equation for the adiabatic process is this one, which means you can also write this as P1 V1 raised to gamma, that is P2 V2 raised to gamma. Now let's apply the chain rule here and find the change in these quantities, just like we did over here. So v raised to gamma, let's take this as constant, then change in this one, plus now p constant. Now x raised to n differentiation is n x raised to n minus 1. Differentiation means the change. So in the same way, this one will be gamma will come in front, then v raised to gamma minus 1. Now the differentiation of this function, that is dv. Now on the other side we have constant, and the derivative of the constant is always 0. Now let's take this on the other side, v raised to gamma dp, that is equal to minus p gamma v raised to gamma minus 1 dv. Let's take this over here, so dp by dv, that is equal to, let's take this over here, minus p gamma times v raised to gamma minus 1 upon v raised to gamma. So this is dp by dv, that is equal to minus p, this goes up, v raised to gamma gets cancelled. So basically this part is 1 by v. So this is gamma times 1 by v. So this is gamma times minus p by v. Okay. Now what do you think, what would be the nature of graph of p versus v in case of adiabatic process? So I would like to stress something over here, that again, since the pressure and volume are inversely proportional, you can see that two quantities product is constant. So one is inversely proportional to the another. That means if I increase this, this is going to decrease. So just like something over here, two quantities which were like proportional to one another indirectly, in the same way over here they are also going to be inversely proportional. So that means the graph also will be hyperbola, but the slope of this graph has to be larger than the slope of this. Look, because gamma is a quantity, that is ratio of Cp by Cv, and gamma is always greater than 1. So if you look carefully, this minus p by v, here also minus p by v, multiplied by a number that is greater than 1. So the slope of this is larger than the slope of this. I'll have to make the graph more steeper, something like this. It is not going to touch this one, right? It is going to go all the way to infinity like this. But when you draw p versus v graph for adiabatic, and this is isothermal, you always make sure that the graph of this is more steeper than the graph of this. Okay, and the slope of this is gamma times more than the slope of this graph. All right. Okay, so now since we have talked about the slope, let's talk about two different cases of expansion and contraction in case of the adiabatic as well as the isothermal process. So I'm going to go draw two different graphs, but please understand, you are going to very easily understand this. So do not have a fear of any kind of problem with respect to this topic, right? So this is p versus v graph. This is p versus v graph, again p versus v graph, right? And this time I'm going to have a gas at state A. That means it is going to have some pressure, some volume and some temperature. Now the gas is going to expand. That means the volume increases. So let me draw something like this. Now let me call this process as isothermal. Isothermal what? Isothermal expansion, because you can look very carefully, the final volume is more than that of the initial volume. So I have taken finally a gas to a state B by the isothermal expansion process. So if I say that the pressure here is P1, volume here is V1, then here pressure is P2, volume is V2. V2 is greater than V1, but P2 is smaller than, P1 is greater than P2, because when volume increases, pressure has to decrease at constant temperature. But the same gas, when it is taken adiabatically from state A to state B, the graph has to be something like this. This will not touch this axis, but I mean to say that the graph has to be more steeper, because just now we have seen that the graph of this adiabatic process is more steeper than the graph of isothermal process. For the same volume, this is, let me call this point as C, you can very well see that from A to B, the area, I must say, the area below the isothermal graph, that is this much big. So the work done by the gas when it expands, or work done by the gas is positive, which is the area under the graph, and you can see the area to be very, very larger. Compared to which area? The area in case of the adiabatic graph would be only this much. I hope you are understanding this very well. This checkered area, this area, and area is always under the graph. So in both the cases expansion, so in both the cases work done is positive, but more area is under the isothermal curve. So you can generally state from here that work done by gas in adiabatic expansion is less, adiabatic expansion work done is less than isothermal expansion. So simply I can say work done by isothermal is more than the work done by the adiabatic, but this is in case of expansion. Now let's compress the gas and try to understand the same phenomenon. Always understand that the slope of isothermal has to be larger than the slope of the adiabatic. So let me say I have a gas at state A and it already has some volume, say V1. Now I want to compress it, so the gas is going to get compressed and the final volume will be less than this one, so the graph will go backwards. And when the volume decreases, the pressure has to go high, so the graph would be something like this, curved one. And finally the gas reaches to point B and you have to mark the arrow showing the compression process. Now the final volume, let me call this as V2, final pressure is P2, here pressure was P1 and volume was V1. Since V1 was greater than V2, so the pressure P2 has to be greater than P1, inversely proportional. Volume decreases, pressure increases. So you can very well see that in this process, this is the work done on the gas, or this is basically the work done by us in compressing the gas. So this is work done by us in which process? Isothermal process. Now just imagine what is going to happen in adiabatic process. The graph has to be more steeper, so the slope of the graph has to be steeper and the graph will go somewhere over here like this to the same volume state. If you want to make it go, then the graph has to be more steeper, and you can very well see that now the area under the graph is very, very large. So the work done by the isothermal process, work done by us during isothermal process is less than work done by us or work done on the gas in adiabatic process, right? So here the gas is doing the work. So when you isothermally expand the gas, the work done is more compared to when you expand the gas adiabatically. But here when we compress the gas, we have to do more work in compressing the gas through adiabatic process with respect to the isothermal process, and the graph states very clearly in both the cases you only need to understand one thing, that the slope has to be always larger for the adiabatic process. So this one was for adiabatic and this was for isothermal. I hope this video was helpful. Please comment in the comment section if you have any doubts. Thanks for watching.